So a very good morning to all, and I would like to start the class on calorimetry, and this is lecture 2. So in lecture 2 we are actually going to study about the principle of calorimetry. So the heading will be principle, and I hope everybody is copying it down, and please to have a notebook in front of you when you're doing this lecture. So principle of calorimetry. So as we know, calorimetry is what? The study of heat transfer and also the measurement of heat, we can say. Okay, so principle of calorimetry, we also say like POC. So what is POC? POC is, first thing you should know, it is based on the law of conservation of energy. So heat, as you know, is a form of energy. Okay, so heat is a form of energy, and temperature is what? Temperature is an expression which we use to represent the average kinetic molecules of all the average kinetic energy of all the molecules present inside a body. Okay, so in principle of calorimetry, what you need to learn is that this heat which is lost by a hot body is equal to the heat gained by cold body. Now the tendency of a cold body is to absorb heat and increase its temperature. So absorption of heat, releasing of heat, these are all forms of transfer of heat, right? Now heat is a form of energy, so energy can be transferred from one body to another without any loss. You know that, like according to principle of conservation of energy, that is where conservation is coming. That energy is conserved, it is not being lost. Okay, and a hot body has a nature or a tendency to lose some amount of heat. Okay, now under this principle of calorimetry, you have to remember this one principle only, which is heat lost by a hot body is equal to amount of heat which is gained by a cold body. So you will write Q lost by hot body equal to Q lost, extremely sorry, Q gained. It will be Q gained by cold body. Okay, and I hope you remember what was the formula of specific heat capacity. Specific heat capacity. Can anybody tell me the definition? What is the definition of specific heat capacity? Okay, so specific heat capacity is the amount of energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius. So here we are mentioning the unit mass. Unit mass means 1 gram, suppose. Okay, so unit mass, for a body of unit mass, the amount of heat which is required to raise its temperature by 1 degree is known as specific heat capacity. So what was the formula? Q equal to mc delta T. Now delta T was change in temperature, m was mass of the body, good, it was mass of the body, and what was C? C is specific heat capacity. So the formula for heat is equal to mc delta T. So if we transverse this, we can write C equal to Q divided by m delta T. So either you remember Q equal to mc delta T, or you just remember C equal to Q m by delta T. Now there's a difference between heat capacity and specific heat capacity. So let me remind you once again. So what is heat capacity? Heat capacity is the amount of heat required to raise the temperature of a unit mass of substance. But when we don't want to mention or when we just want to measure that amount of heat that is required by a body of 50 kg mass, or you know, a 50 gram mass, we don't want to mention unit mass. So in that capacity, we in that situation we actually mention heat capacity. Okay, So specific heat capacity formula is C equal to Q M delta T. So there is a mention of mass here. Okay, there is small c. It is small c. Okay. Now heat capacity has a formula capital C equal to Q divided by delta T. Q divided by delta T. This is capital C. This is capital C. Okay. So whenever you are told to find this heat capacity, you don't need to worry about the mass of the body. But whenever you're told to find the specific heat capacity, you have to divide it by the mass of the body because specific heat capacity is applicable only for unit mass of a substance. Okay. So with this formula and everything, let us move on to the first sum. Now I have taken the sums from the back of your exercise book only, and later on I will add more sums. Okay. So if you go to the numericals, question number 8, you can see what they're writing. 0.5 kg of lemon squash at 30 degrees Celsius is placed in a refrigerator, which can remove heat at an average rate of 30 joule per second. How long will it take to cool the squash to 5 degrees Celsius? Specific heat capacity of squash is 4200 joule kilogram per Kelvin. Okay. So here, first of all, write down specific heat capacity of what? Squash. It is 4200 joule per kilogram per Kelvin, right? Okay. Now you see, what is the mass of squash? It is 0.5 kg, right? Now what is the initial temperature? Ti. Initial is 30 degrees Celsius. Placed in a refrigerator which can remove heat at an average rate of this much. How long will it cool the squash to 5 degree? So this 5 degrees Celsius is how much? This is final temperature. This is 5 degrees Celsius. Extremely sorry for the bad handwriting. Okay. So this is 5 degree Celsius. So difference in temperature is how much? T final minus T initial, which is how much? 25. Okay, which is 25. Okay. So excuse me. So it is 25 delta T. Okay. So now they're saying, see, how long will it take to cool? That means they're wanting us time. Now from where do we get the factor of time? Here you actually got this remove heat at an average rate of 30 joule per second. Okay. So now through this, they're actually telling you the power of the refrigerator. Okay. Now, if you notice the unit, it is joule per second. Can you tell me which physical quantity has joule per second as the unit? Or we can write joule per second as watt, which is what? Power. Okay, so they're giving you the power of the refrigerator. So from this statement, what you can get is in 1 second, 30 joules of energy can be extracted by the refrigerator from the juice, right? So first step is find out heat, which is Q equal to mc delta T. What was mass? Let us go on to this page. What was mass? It was 0.5 kg. So mass is 0.5 kg. C is 4200 and delta T has how much? 25, right? Yes, 25, 30. Yes, it was 25. So let us now find it. Okay. So mass, let me see, let me check the units. See, mass is in kg, temperature this much, Kelvin. Okay. Now one doubt if I have, which may say ki here it is Kelvin, here it is Celsius, but you are not changing the units. Actually, when you try to change from Celsius to Kelvin, you add plus 273 both ways. So when we actually deduct, it becomes the same. So difference in Celsius is equal to difference in Kelvin. Okay. So be careful about this. Whenever you're doing a difference in Celsius, it actually is equal to the difference in Kelvin. So you don't need to change the units and waste your time. Okay. So straight away find out mc delta T, which is amount of heat which is there inside the your this thing juice. Okay, so this is the amount of heat which is there. Okay, now the refrigerator can extract 30 joules of heat in 1 second. Therefore it is now just simple unitary method. See, 30 joules can be extracted in 1 second, right? So 1 joule can be extracted in 1 by 30 seconds. Okay, now let us look at this figure. 0.5 into 42 into 25. Okay, so 0.5 into 42 into 25, and this is 4200. Sorry, this is 4200 joules can be extracted in 1 by 30 multiplied by 0.5 into 4200 into 25. So this is 5, this is 6. Now 6 7 is 42, you all know that. So here I can write 0.5 as half. So here write 350, and 5 zeros are 0, 5 5 25, and this is how much? 15 16 17, 1750 seconds. Okay, now if you divide 1750 by 60, you will get in minutes. If you further divide it by 60, you will get in hours. Okay, so this is how you will solve the sum. Okay, so now let us come to sum number 9, which is, if you see, the mass of a 50 gram of a certain metal at 150 degrees Celsius is immersed in 100 gram of water at 11 degrees Celsius. The final temperature of the mixture, I guess, mixture of what you will ask me, which is metal plus water, because see, when you're putting this hot metal into water, what is happening? The temperature of water is rising from 11 to 20. Simultaneously, temperature of the metal is also falling from 150 to 20, right? Okay, so calculate the specific heat capacity. So if you see, the temperature change of metal is 150 minus 20, right? Now delta T for water, it is how much? It is 20 minus 11, because from 11 it is rising to 20, and from here 150 it is falling to 20. Okay, so if you see, the heat which is lost by this is actually the heat which is gained by this, which is the water, because in this case this is the hot body and this is the cold body. So I hope I am clear. So now use the formula of heat, which is Q equal to mc delta T. So now m is how much? 50 for metal, and C I don't know, I'm taking it as X. You can also write let the specific heat capacity be X joule per kilogram per Kelvin. Sorry, write down per gram. Huh? It will be easier for you. Don't write kilogram, write down per gram, because everything here is in grams. So that is why I write down grams. You don't have to convert anything. So X into T, delta T is how much? See, 150 minus 20, because this is final. This is sorry, this is the difference. Don't say a final initial, because you will get confused. Just say the difference in temperature is this much. Okay, which is equal to the heat gained. So let me write it with a blue pen. So this is how much? This is your C. It is 100 grams. So 100 grams into this is how much? They have told 4.2, as we know, into difference 20 minus 11. Okay, so here cut it by 2. Okay, so when you cut it by 2, what do you get? X multiplied by 150 minus 20 is how much? 130 equal to Z. This is, you can multiply, just keep it like that. 2 into 4.2 into 20, it is 9. So X is how much? 2 into 42 into 9, I'm making this 10, 130. So if you calculate, you'll get the answer from here, X. Okay, so X will be the specific heat capacity. Okay, now let me move on to the next one. Another sum is there, I guess. There is the sum. So yes, so 200 gram of, did I miss sum number 10? I guess I missed sum number 10. So please do look into sum number 10. If there is any difficulty, please do tell me, because I think I have missed sum number 10. This is sum number 12, sum number 13. Okay, so a lot of sums is left. Let me move on to this sum. 200 gram of hot water at 80 degrees Celsius is added to 300 gram of cold water at 10 degrees Celsius, neglecting the heat taken by the container. Calculate the final temperature mixture. So when they have told neglecting the heat taken by the container, we won't actually get involved in calculating the amount of heat which is taken by the container, because it is definitely that when they're mixing the hot water, first there's a container. Okay, so first there is a container in which they're pouring hot water, then they're pouring cold water in it, then these two mixtures are coming at a final temperature which they have told, I guess, oh, they have asked us the final temperature, they have asked us to calculate. Okay, so final temperature they've asked us to calculate, and this is what we are going to find out. So they took a container, they put hot water, then they put cold water, then both of those it got mixed, they formed a final mixture which at a final temperature. So that is what we need to find out. Okay, so in this thing, okay, I made a mistake, which is in this thing you have to think of this very carefully, and let's start the sum then. Okay, so see here hot body, here cold body. See final temperature, let the final temperature be x. Okay, let the final temperature be x. I'm just containing it, considering x degree Celsius. So hot body is of 200 grams, has a temperature of 80 degrees Celsius. Cold body is of 300 grams, has a temperature of 10 degrees Celsius. So if you see temperature difference between this, from this it will come down to this. So it was 80, right? It will come down to x, hot body will come down. Okay, and for the cold body it will come to this final temperature of x from 10. I hope you understood this. From 80 it will come down to x for the hot body, because hot body will lose this heat which will indirectly be gained by the cold body. So cold body will raise its temperature from 10 to x. Understood? That is the x here is the final temperature. Okay, okay, so here you see q equal to mc delta t, here also q equal to mc delta t. So here mass is how much? 200. C is how much? Have they given us C of 40? Yeah, 4200. Let us do one thing. See, both sides C will be similar. So I'm just taking C only. Okay. Now here it's 80 minus X. Here it is mass is how much? 300 gram into C I'm taking, because ultimately it will get cut out, because both sides 4200. Don't have to waste your time writing that. Okay. So here X minus 10. Now let us take a new page and just settle this thing down, which is 200 into C into 80 minus X is equal to 300 into C into X minus, what was the temperature? 10. Okay, so C and C gets cancelled, 0 0 from here, 0 0 gets cancelled. So 80 minus X, okay, multiplied by 2 equal to 3 multiplied by X minus 10. So 160 minus 2x equal to 3x minus 30. So 3x plus 2x equal to 160 plus 30. So 190 divided by 5x. So x equal to 190 by 5. So 3 5 is 15, you can do 40. 8 5 is 40, right? 3 5 is 15. 40, it was a 40, 38. So x is 38. So maybe 38 is the Celsius is the final temperature. Okay. Now method of mixtures is just like this. Now see what they're saying. In method of mixtures, you have to actually this thing assumption. Whenever you see there's an assumption. Whenever you see this kind of sums where there is a method of mixtures, uh, like I said, key hot body was put in a container first, then cold was put. So a question may come, ki suppose this vessel is made of copper. Now copper has a heat capacity of 0.4, we know that. So it has some heat capacity, right? So when you're putting hot water, the hot water is there, right? Now the copper vessel is actually also gaining some heat from the hot water. Now this is where the assumption will come. What is the assumption? You remember one thing. As soon as hot water is poured into the vessel, remember this very carefully, temperature of vessel will become equal to the temperature of the hot content within it. Then it will come to the final temperature of mixture. That means when you initially put the hot water inside, the vessel will also get heated up. Okay, now again when you pour the cold water inside, now that vessel will actually gain the average final temperature. That is the final temperature. Just leave average but final temperature. Okay, understood? Okay, so let us look at this sum. Okay, the temperature of 600 gram of cold water, what they have said, the temperature of 600 gram of cold water. Okay, so the temperature of 600 gram of cold water, they have said, extremely sorry, of cold water is water raises by 15 degrees Celsius when 300 gram of hot water at 50 degree Celsius is added to it. What was the initial temperature of cold water? Okay, this is not a sum of mixture, I guess something has, the sum number has flipped from here to there, don't mind. So let me focus on this sum only, which has come forward. That is question number 12. The temperature of 600 gram of cold water rises by 15 degrees Celsius when 300 gram of hot water at 50 degrees Celsius is added to it. Okay, so see, hot body, which one is the hot body? 50 degrees Celsius one water. Okay, which weight is this much, and water ka heat capacity is how much? 4.2 joule. Okay, unit per Kelvin per gram, not kilogram. If it is kilogram, it will be 4200. Okay, okay. So hot body is this one. This is cold body. Cold body is how much? 600 gram. And temperature is how much? Okay, so it raises. So let me consider temperature as x degree Celsius. Okay, now from x, it will become how much? X plus 15. Right, it will become x plus 15, because what they've said, when you will actually mix both, then the actual final temperature will be raised. The final temperature of cold water will be raised to x plus 15. That means 15 degree more than the initial temperature of the cold water. Okay, so temperature of 600 degrees Celsius, 600 gram of cold water, very sorry, by 15 degrees Celsius when 300 gram of hot water at 50 degrees Celsius is added to it. Okay, okay. So now here, see, hello. Okay, so let us come back. Q equal to mc delta t. Here also Q equal to mc delta t. Okay, now see, temperature of water here, difference will be how much? From 50 it will come down to x plus 15, so this will be delta t. Okay, and here delta t will be how much? X plus 15 and minus sorry, not 15, extremely sorry, it is x. Okay, so now here q of hot body go to q of cold body, so q will be how much? Let me go back, it's so tedious, right? So 50 gram is there, right? Yeah, gram Sorry, 50 degrees Celsius. What am I doing? It's quite late, so I guess a little bit overwork. Sorry for that. Okay. So it is of 300 grams and both are water. So C I can take. It is how much? 50 minus x plus 15. I have to get a second bracket here. And here it was how much? It was 600. So whole body is 600 multiplied by C I can take because it is water itself, and it was x plus 15 at the final stage from x. So x gets cancelled from here, 0 0 0 0, and this gets cancelled, 2 cc gets cancelled. So this is 15 minus x minus 15 equal to 2 into 15. So here 15 minus 15 is how much? 50 minus 15, 35 minus x equal to 30. So 35 minus 30 equal to x. So x equal to 5. Okay. Now everything was in Celsius as we calculated. So x equal to 5 degrees Celsius. Therefore, this is the initial temperature of cold water. Okay. I hope I am clear and I could explain this to you. This is the last sum for today. So 1 kg of water is contained in a 1.25 kilowatt. This is the unit of power. Power means joules per second. That means in 1 second, how much joules you use, that power can show. Okay, so calculate the time taken for the temperature of water to rise from 25 degrees Celsius to its boiling point 100 degrees Celsius. Here the question is very simple. They're saying they have a kettle of some power. Now what is this power doing? It is supplying heat. Now how much heat do you require? You require that much of heat which is sufficient to raise the temperature of 25 degrees Celsius of water to 100 degrees Celsius. You require that amount of heat which will be sufficient to raise the temperature of water from 25 to 100. Okay, so how much heat do you require? MC delta T. You can find it by MC delta T. So what is the mass of water? Have they told you 1 kg? So 1 kg means I can write it in grams. Why I'm writing it grams? See here 4.2 is mentioned in grams. That is why I will do what? I will change the kg to gram. Okay. So here also you can do the kilowatt to watt, you can change, and it will be very easy. I'm just doing it. See what is how much? 1.25 kilowatt. This is unit of power. Okay. So 1.25 multiplied by kilo means 1000. So multiplied by 1000 and you will get watt. Just keep it like that. So M is how much? 1000 gram. C is how much? 4.2. Delta T is how much? 75. 75. This is the amount of heat that you will require in total. Okay. Now the electric heater can provide 1.25 kilowatt or 1.25 into 1000 watt per second. Achha, it will not be watt per second. Extremely sorry. It will be joule per second. Yes, it will be joule per second. So in 1 second, achha, in this way you don't write unitary method. You always have to write what? 1.25 into 1000 joule in 1 second. So 1 joule will be given in 1.25 into 1000, right? So now if you see here, this much amount of heat, 1000 into 4.275 require. So 1000 into 4.2 into 75 is what you require. So 1.25 into 1000 into 1000 into 4.2 into 75. So this is the reason I was telling you not to cancel. So from here you do one thing, 4.2 you can write 42 by 10, and 1.25 you can write here 100, so it becomes 125 for you. Okay, so here from here cancel, I'm just making the calculations easier. So from here it is 125, so 25 fives are, so 25, here 2 is there, here it is 3, so ultimately 6 into 4.2, sorry 6 into 42, so 6 2 is 12, 24 25, 252 seconds. If I made some calculation error, please do look for it. And if you like this lecture, definitely do let me know. And if you have any doubt, you're free to ask me on WhatsApp. And a big thank you to you all for listening to this lecture. Keep smiling. Thank you. Bye.